everybody. So today I'm going to present you this study that we call Quantum-Centric Computational Modeling for Meta-Organic Frameworks in Carbon Capture. It's a collaboration between Capgemini, we have done the technical work, and Total Energies that they have advised us how to steer the project toward an interesting direction. And I think it's proper to start, well, I assume everybody is more or less familiar with the problematic of climate change. I just want to mention that, of course, it's a pressing issue. And the most, carbon dioxide is the most important gas, greenhouse effect gas associated with human-induced climate change. And so we need to develop methodologies, technologies that can remove carbon dioxide from the atmosphere or from the sources that are emitting carbon dioxide. And carbon capture is one of them. The idea is very simple. You just physically remove the carbon dioxide from those sources or the atmosphere, and then you store that carbon dioxide underground, or even better, you can convert into something that is useful, like, for example, a fuel. One of the materials that have been proposed in order to perform this kind of carbon capture is metal-organic frameworks. This big boy on the right is a metal-organic framework. The idea is these molecules, they have pores, they can absorb different molecules, and you can tune them. You can change the linker, you can add other organic groups, you can change the metal, you can tune those pores and the interactions that are going to happen inside, and then they can selectively absorb one molecule or another. So that's the reason we were interested in this project, not because it's a very interesting subject, it's a real subject, and we were interested if we are able to develop a way to use quantum computation now or in the near future in order to tackle this type of problem. So the project has been carried out in the Capgemini's Quantum Lab. That is a group of researchers from different arms of Capgemini that we are working with partners in industry, government, academia. And the idea is we are trying to bring quantum computation to different research fields. The funding comes from DARPA. It's a federal agency from the United States, from the Defense Department, and the funding opportunity was in PAC. So DARPA really is not interested in carbon capture in this funding opportunity. What they are really interested in is seeing how would you use a quantum computing for a real case scenario if you could. So DARPA is more interested in how we are going to apply the quantum computer, how transferable our approach is, things like that. So I mentioned this is a carbon capture project, but in a sense it's not. It's just the application we chose in order to use quantum computers or envision how to use quantum computers. Of course, we have a problem. So meta-organic frameworks, they are huge. In general, real relevant systems, they come in all sorts of sizes. But we also know that current quantum hardware cannot handle large systems. So the first approach that will be just feed this system to the quantum computer, of course, is not going to work. So the only way to do that, or the only way we think we can do that in a relevant way, is just to decrease the size of the system, but we decrease the size of the system in a way that we end up with a model that is still relevant, it's small enough to fit now or in the near future in a quantum computer, but that's going to still give you relevant information about the large original system that you have there. We call that a process of reducing the size but staying relevant. So how we do that? And what we do is just, we are going to apply a series of tire and test, others a little slightly newer approaches that basically they are divide and conquer approaches that are going to break your system into smaller fragments and allow you to work with those fragments in an independent way. So we have an end-to-end computational workflow that does that, and the workflow is highly transferable with minimal modification. As I mentioned, it's based on a series of approximations and divide and conquer methods, like standard computational chemistry divide and conquer approaches, chemically sound approximations, and physically sound approximations. What do I mean by that? Let's see step by step. So the first thing we do is we are going to divide our system physically. And we are going to apply a hybrid approach. Those approaches are well known in the literature in computational chemistry. We end up then with two subsystems. We have a model, a very small model that we intend to fit to quantum hardware, in a sense. We will see how. And then we have a larger structure that we intend to compute with classic hardware. The idea is this large cluster is going to give us only information, secondary information about how the bulk structure is influencing the interaction between the metal-organic framework and the carbon dioxide. And there are different ways that we could have done that. We could have used molecular mechanics, DFT, or DFT with periodic boundary conditions, for example. We decided to use DFT, but those systems are very big. So luckily, we have access to a software that runs DFT in GPUs and is very well optimized and allow us to compute not only this type of clusters, but even larger clusters to see if the energies we are getting of the environment are already converged. The good thing is this is completely independent of the other branch. Now we have a much smaller system. That is the one that we intend to compute in a quantum computer. But this system, this model that is going to give you finite information, detailed information about the interaction between the metal-organic framework and the carbon dioxide is still too big for quantum computing. So what we do next, we apply a new divide and conquer approach. In this case, we decided that we wanted to apply at this point an embedding methodology. An embedded methodology doesn't physically break the system, but divides your large calculation into a series of smaller calculations on fragments, and then from those fragments, you can reconstruct the energy of the cluster that you are interested. In this case, we're going to use the weight function-based embedding theory. One of the things is WF. One of the things that we want to use this approach is because we can use atomic-like fragments. That is very interesting for us because also remove one of the problems when you have this kind of methodologies, is how are you going to fragment the system? In this case, you can use atoms, and also they are very small. Now our problem is we are turning just one calculation into something like 30, 40, 50 atomic calculations, and those are many calculations, especially if we are going to send all of them into a quantum computer. So what do? So we applied our chemical intuition. So we know in chemistry is very local. So only the atoms that are very close to the point where the metal-organic framework and the carbon dioxide interact, only those atoms are going to be the most relevant ones. So we decided to group the atoms in terms of first and second class atomic fragments. First class atomic fragments are in red, are the ones that are going to be very close to the interaction. Second class atomic fragments are the others and can be computed using classic computation, classic hardware, and a lower methodology. So now we have just only a handful of atoms that we intend to compute in quantum hardware, but those fragments are still large. I said that EWF allows us to use atomic fragments, but one of the reasons allow us to use atomic fragments is because it's strongly coupled those atomic fragments with its environment. So include a bunch of orbitals from the environment. So the calculation is not as cheap as it sounds. But that coupling can be controlled. So we apply here a physical approximation where we thought, OK, let's consider only atoms that are weakly coupled with the environment. Those are going to have an active space that is much smaller than the ones that you need really to get the converged energy. And what we are going to do is going to compute a correction of the coupling using a classic methodology and using HPC. So at the end, we end up with a bunch of what we call weakly coupled atomic fragments that are the ones that we intend now or in the near future to send to quantum hardware. That's the whole workflow. Yeah, the first thing we did is we believe that there is a lot to learn by doing still classic computation, mimicking what would you do, what you will do if you have a quantum hardware available. So I have some results here that I want to comment very briefly. So the idea here, we are only using the high-level cluster, and one of the things we did is what happens if we just run DFT there? That can be a baseline model. And what we see is one of the problems with DFT. If you use the right density functional, you get astounding results in green, just like chemical accuracy, just very cheap. But do you know that that's the right functional? No. You may try one of the others, and if you use the ones in red, you get bad accuracy. And if you use the other one, you get something that is so-so. One of the problems with DFT is now, how do we improve this result? We need to better accuracy. There is no clear path. It's what happens with DFT. There is no clear path for improvement. You can try another functional. It's going to work well, or it's going to work worse. Then we applied what we call an EWF recipe. And the idea, this is like a multi-level approach that is based on all the fragmentations we did before. So there is a lot of things that can be tuned here. So we tried a few combinations. And what we see is, while all of them, they can beat the functionals that don't work properly, none of them can beat the functional that works the best. But for us, the main result here that is interesting is such a complex formula that even one of those approximations that we are applying is wrong, the numbers should fall apart. So the approximation at least makes sense, and it also indicates that if we do these methodologies, we can achieve higher accuracy. First, for example, only the last term is the one that we will intend to run in a quantum computer. And here we're using Capet cluster SD. We could have used a higher methodology, and we will get better results. As we know, it's basic physics. Another thing that we can learn from running this type of calculations, and I'm going to try to go a little fast here, is that we can learn the size that these EW recipes, the size of the fragments that we need to compute eventually in quantum hardware. And here, for me, the takeaway is, depending on the approximation and the recipes you are using, we are going to need, let's forget about error rates and things like that at this point. Let's adopt a naive approach. Those calculations, just based on the number of logical qubits that you will require, just assuming a mapping of 1 qubit, 1 spin orbital, should be able to fit in quantum hardware that is coming in the next 5 years. So the idea is, it doesn't matter the size of the system you have, you're going to break it finally into atomic calculations, and those atomic calculations, they have a more or less fixed size that, in terms of the number of logical qubits, they will fit in the hardware that's coming. Of course, a less naive researcher than the one that's talking here will tell you, yeah, but you are just going to have the problem with how deep the circuits are. Probably we will need very deep circuits. But I just want to mention that 5 years is very far away. At this point, yeah, we will need very deep circuits, but the methodologies are improving. The algorithms are improving. With BQE, probably we will never be able to run something that requires, I don't know very well how to, perfect. Something that requires something like 30 logical qubits, because the circuit is so deep that you cannot run that. But maybe in 5 years, we're applying BQE, or we are applying a version that is more efficient than what we try here, that is adapt BQE. So also, there are many more approximations that you can take from classic computational chemistry that we can still apply to those numbers in order to reduce the size of those active spaces. So at this point, I feel very positive about that. Of course, we try to do some quantum calculations in real hardware, and I'm not going to talk much about it because the first thing is we knew they didn't fit, so we have to reduce the active space, and this is kind of like a betrayal of the whole approach. The whole approach is work until you reduce the active space to the minimum and then send that to the quantum computer. Of course, the minimum we achieve is not just sufficient to run in current hardware. So what we tried is just to run with some limited active spaces, and we saw the same problems that everybody is seeing. No, like the circuits are too deep still. Yeah, basically what everybody is seeing. Nothing new here. But I want to conclude so to speak, in a happy note, expressing that what we have achieved is that we have an end-to-end workflow to incorporate quantum computation into computational chemistry studies, and thus the size of the system is completely relevant. That workflow is also highly transferable. And also, our studies using just classic computation indicates that at least in terms of the size, in terms of the number of logical qubits that we will need, those sizes can run potentially soon within 3, 5, 10 years in quantum, well, maybe less than that. Especially if you focus, probably I should have noticed that, if you look at the end of that table, you will see that organic chemistry is much easier to compute than organometallic chemistry. Metals always require higher active spaces, while organic chemistry, first elements, row, they also require something that is about 20 for the first approach, 25 logical qubits. And that's a better candidate than organic chemistry to be computed using quantum hardware in the near future. To mention of our quantum calculations, we found a variational hybrid algorithms such as ADAPT-BQE don't scale well in practice, but sample-based quantum diagonalization is one of the methodologies that we want to try now. Using samples from circuits offers a more practical approach that can scale to larger active spaces and fits more naturally with the wave function-based quantum embeddings that we are using here. That concludes the presentation. Thank you, everybody. Of course, if anybody has any questions, please feel free to reach out to anyone that you see in that table. We will be more than happy to answer any questions or direct you to the right person to answer the question.